Log on, tune in, find out. Another good idea from Cambridge.
Our final speaker in this session is Vincent Agboto. He's from Meharry Medical College in the USA, and he's talking about a comparison of three approaches for constructing robust experimental designs.
Hello, my name is Vincent Agboto. I have to say that it's an humble experience to follow the two previous speakers that have been associated somehow with me for the last more than 20 years, I would say. I remember that in 2000, when I was a graduate student, it's just a little story. At the University of Minnesota, I decided to come to a conference at Ohio State University. That was chaired by Angela Dean. So she gave us some grants with some friends and we came. Then I saw William Lee and Chris Neinstein give a good presentation there. So I noticed, oh, they're from the University of Minnesota. Then I've been stuck with them since then. So Chris Neinstein is my advisor, and along with William Lee, so they're my mentor, and so that's how I've been in the design field. And since Chris is closely correlated with Brad Jones, I happen to see Brad Jones quite a bit too. So that's the story, and that's how I'm here. So I want to thank everybody for being here. So it's in this talk, we're going to give a small introduction and motivation, and then we're going to present three approaches to what we call design robustness, and then we're going to compare some. Going to do some empirical comparison and make some conclusion. So the main idea here is about model dependency. Typically, in a typical design setting, you have a model and then you have some criteria that fit that model. But in many applications, the model is not, the true model is not necessarily known. Okay, so it can be assumed that the true model, in this case, is an unknown set of known model. Instead of setting a model, saying that this is our model, and then we fit the criteria, and then to get a design based on that model, instead we have a set of model, and then we know that the true model is somewhere there, and we try to find a design that. Sorry about that. We find to start a design that is efficient over the class of this model. So that's the issue of what we call the model robust design. And it's an area that is good. Sorry, I'm just gonna put it in my pocket. It's an area that is gaining some popularity. And here we're going to introduce a new Bayesian models robustness design. Then we're going to compare it with a design, model robust design criteria that was used by Lee and Neinstein, and then another one used by Dumichel and William Jones. That's why I call DJ. So that's a quick notation here for design matrix, and then we're going to have a set of model from which we're going to derive our design. And then we have the model matrix, which is different than the design matrix. So the design matrix is this, and the model matrix is comprised of the actual effects that are present in the model, while the design matrix is comprised of the main effects. Okay, so there is also that we're going to consider the linear model assumption here. And then we have a notation about a set of model, which is a possible model having n-1 or fewer main effects, where n is the run and m is the number of main effects. So first of all, I'm going to introduce the approach of Lee and Neinstein. So typically what they did is they have a set of model. Then they came up with this criteria, which is just maximizing the weighted average of what we call some sort of efficiency. Now, this efficiency can be what is estimation capacity, just to see whether those models are estimable or not. If it's estimable, it's 1. If it's not, that's 0. So we come up with some percentage which tell us whether these criteria lead to estimability of in that set. And then we also have the information capacity. So it's a paper by Lee and Nastine. So then in another paper by Dumichel and Jones, what they have is they have a model in which they consider some effects primary term, and then so those effects are assumed to be present in the model, and then they consider the other one potential term, which could be or not in the model. So they came up with a criteria, this criteria here, and then with this matrix. So that's what it is. Then those are the previous ones that were done before. Then we came up with this one here, the Bayesian model robust design. So this approach basically is based on the idea of the standard Bayesian design. Now, in a standard Bayesian design case, we have a single model, and then we use the callback information to compute the criteria. But now, instead of a single model, we have multiple models. And then there are prior information, prior probability associated with this model based on how plausible they are in the model sets. And then we also assume some prior distribution on the parameters. So based on that, and with an assumption, this assumption here, then we have this criteria. That is the new criteria of model robust design that we came up with. And this criteria, if we just went back to a single model, with it comes back exactly to the standard Bayesian design. Okay. So now the idea is to see whether we can create design based on this model and see how those designs do with respect to the 3 criteria that we just listed. Criteria based on the Lee and Nastine, criteria based on the William Dumichel and Jones, and then this one that we came up with. Okay. And it's a joint work with Lee and William Lee and Nastine. So now, this is we're gonna consider a set of model space in order to test our criteria. So the first model space here, this model space is just a model of M main effects and G 2-factor interaction. So standard criteria might be typical case where here we have, let's say, when M is equal to 5. So we have A, B, C, D, E, and then 2 standard, we have here 1 G, that means 1 2-factor interaction. So we have the plausible model in that set are A, B, C, D, E, A, B. A, B, C, D, E, A, C. A, B, C, D. So all this possibility of 5 main effect and 1 2-factor interaction. So those are what we have. So in this model space, we consider this design here. So we consider this, that's the fractional factorial design also that we consider here. Typically just because this is the standard approach that is used in this, typically in this case. So we compare this with regard to the estimation capacity, the information capacity from Lee and Nastine, and then our approach, our criteria, the Bayesian model robust, and then the Dumichel, and then we see whether the design that we came up with are balanced or not. So when we look at this, we notice that for our Bayesian optimal design criteria and the Lee and Einstein design using the estimation and information capacity, we have for the estimation capacity, we have all the model are estimable for our approach here and Lee and Einstein approach. And then for the other one, here, our does as well also, pretty well, as much as this one here. And then for the model robust design, we have the value that are almost close. And for same for the John and Dumichel. But we notice that in terms of balance, the fractional factorial design is balanced, and then the Dumichel, John and Dumichel is balanced. So now, if we move to the same thing here, now with some variation in the number of main number of run, number of main effect, and then here we have 8 run, 4 main effect, and 2 two-factor interaction. So typically, model space where we have something like A, B, C, D, A, B, A, D, A, B, C, D, A, B, A, C, so on and so on. So a model set like that. And then here we have our 3 design criteria. I came up with design that gave these values here. So since all these values are, the criteria is about maximization. So the higher, the better. The higher, the better. So when we look at this, we notice that for the most part here, our criteria have many values close to the Dumichel and John. Even though here it beats the Dumichel and John a little bit, for the most part, it have many values close to Dumichel and John. And the Lee and Einstein, they seems to be doing quite well in many instances here. So, so that's the first space that we use. So a model space comprised of main effect and G two-factor interaction. So now we move to another space, which is a supersaturated design model space. The previous presenters have talked about what a model saturated design is. So here, what we have for this, we have the number of run and then the number of main effect, which is the characteristic of a supersaturated design, where the number of main effects is larger than the number of run. So here we have our design criteria, Lin and Dumichel. Here we call it still DG, Dumichel John, but in fact is the Dumichel and John criteria that was extended to the supersaturated design in a paper by Jones, Chris Einstein, and Lin. So, but just for simplicity's sake, we just keep it DNG. But in fact, it's the Dumichel paper, Dumichel criteria that was expanded into supersaturated design too. So we have all this. We have the comparison among this here. So what we see is that it looks like our criteria again seems to be closely having close value with the Dumichel in many instances. In many instances here. So that's what we have. Now, what we just did, what we did in this presentation was to come up with a new model robust, criteria to construct design. but it's an approach that is in fact some sort of a middle approach between the Lin and Einstein and the Dumichel. It's somewhere midway between these two approaches. That's what the new approach is. So now we also did the empirical evaluation of this approach, of those three approaches for constructing model reverse design, using the space of main effect and a set of G two-factor interaction. Just for simplicity's sake, that's why we stayed at two-factor interaction. You can do more than that, but just to make it simple. And in our case here, the design are two-level design with the high and low, meaning +1 and -1. And then a supersaturated model design. So the use of, we see that the use of the robust model paradigm of Lee and Einstein, it leads to substantial improvement, especially in the estimation capacity compared to the Dumichel and Jones approach. But in many instances, all these approach seems to produce the same closed design. So what do we recommend here? So we know that the Dumichel and Jones, it has clear advantage in terms of computation efficiency. That's true. But we think that the use of the model reverse of Dumichel, of Lin and Einstein will be more recommended if the computing time is not a big issue. But in other circumstances, the Dumichel might provide the Dumichel and Jones might provide a faster alternative. So then have a few references, and as you might see from these references, you see a lot of William Lee and Einstein. So since they are my mentor, I constantly need to please them, so that's why I put them there most of the time. So I want to thank you for your time. And
Questions for Vincent?
If you're just putting in one two-factor interaction, it doesn't really matter which one it is. Yes. But if, say, you're putting in two, yes, a model with A, B and AC is, yes, very different from a model with A, B and CD. Yes. It wasn't clear to me whether you were including both possibilities in what you were doing.
Yeah. What we have is, we know that in a typical situation, we know that let's say four main effects are important. We also know that two-factor interaction are important. We just don't know which one. So what we did is we consider all the possible model. So A, B, C, D, A, B, A, C. We consider all the possible models. Yes, yeah. That's what we did. Thanks. Yes.
Any more questions? Thank you very much, Vincent. And join with me, please, and thank all our speakers in the session.